Real-time operating systems, part 3. In this part 3, I'm going to give you a foundation. I'm going to give you some background about threads and context switching. I originally intended to cover the differences between an RTOS and a scheduler, but I stopped and thought to myself, we really don't have the foundation here to explain some of those concepts. So if you don't have a comp sci or computer engineering degree, you might not have never gotten to the level of detail which I'll present here. I'll get into the specifics of what a CPU is doing right down to the hardware level to show you what is a thread and what is a context switch. So I've got to take you through the whole path starting with the source code. Source code is the stuff that programmers write. They write this and put it in a text file, and a programming language specifies what the rules are for what you put into into the source code, what you put into the programming language. And there's certain things that are considered errors, and that compilers, and I say compilers, that includes linkers, compilers take this source code and they generate the executable programs that actually run on a computer. I say computer, that isn't quite correct, on a CPU. The source code, it tells the compiler what you want to do, and the compiler takes the source code and makes the machine code which the actual computer uses. And here's an example of what the compiler did. So in black is the stuff that the programmer wrote, the stuff in C. This is a C function call called NUFR kernel add task to ready list. This source code is given to the compiler. The compiler generates what you see in red here. Now there are 3 columns that the compiler, that describe what the compiler generated. The compiler generates the second column starting with the B530, the column in the middle. These numbers are hexadecimal numbers, B530, 4924, 7FC3. And these numbers are the machine code. The machine code is the exact numbers and the exact sequence they appear in. Now the column on the left, the far left, 801078C, these are the addresses that these numbers are put at. So when this is loaded into Flash, and in this case these particular platforms that I'm talking about, products, will execute their code out of Flash, and because they're firmware embedded products, whereas if this were a software product, it would take these instructions and load them into RAM. But these addresses are Flash addresses, and they indicate where the numbers are put. So this third column, it has a human readable form of the machine instructions. So B530 isn't readable. The push R4, R5, LR, that's human readable. So assembly language or assembler code is a human friendly as you can get, way of describing, controlling, and specifying machine code. Machine code is way too tedious for people to work with. So the assembler code is the next step up in automation without getting away from the control and the specifics of what's going on at the machine code level. Now, that previous slide, I've taken out the black and just left the stuff in the red, because when the CPU is executing, it doesn't know anything about that stuff in the black. It only looks at the stuff that the compiler generated, the stuff in the red. If you have a PC, for example, this code in the red is going to be your .ex, the contents of your .exe file, your executable. But the CPU is a machine, and it has specific programming hard-coded into it where it will start at a particular address. Now, this 801078C didn't actually start there, but I'm just picking up a execution in progress. So the CPU will grab this number B530 and decipher it into a machine instruction. And that instruction, of course, is the push instruction. After it does what that push instruction tells it to do, it will then go to the next address, 801078E, and it will take the next number out. And these are 16-bit numbers in this case. And this is an LDR instruction. The machine goes and does that, and it repeats 801070. It sees 7FC3 and just repeats one after the other. And this sequence that the CPU goes through, this is the essence of what a thread is. Now, let me qualify this a bit here. The sequence that I showed you in that previous slide is one instruction after another. When a programmer is writing a programming language, he doesn't just write one instruction after another. There are a variety of things that he or she can specify in order to change and redirect the simple sequence of execution. So, in other words, this dotted line in yellow shows that the CPU is running around in what we call a loop. So it will execute these statements. When it gets to the bottom, it'll go back up to the top, execute it again, go down the bottom, execute at the top, and go around and around in a circle, repeatedly executing the same instructions that it got done doing until it reaches a certain instruction that says, okay, you're finished now. You can jump to another location. So as it's going around in this circle, it is looking at one memory address after another, and then all of a sudden it's told, jump back up 10 locations or so. So that source code example I just showed you is easier to illustrate with the machine code. So this is what the machine is actually doing for that previous slide of the loop. The CPU grabs an instruction here, and this is the 2900 does a compare, and if the result of that mathematical operation is I believe a 0 in this case, it will then tell the CPU, I don't want to execute the next instruction. I want to jump back up in memory. So this 801008, which has the D0, D9, the next instruction could potentially tell the CPU, don't go to 801080A like you normally would, but jump up to an earlier address. And that earlier address is the one on the right after the BEQ.N. It's the 801007BE. And it will jump around like that. And of course, if it doesn't jump up to 801007BE, it will continue on and execute the 7FCC, the 429C, and then again it gets to the D903. D903 is another conditional branch instruction. The CPU will look at the condition and decide whether it will jump down to this 460A or not. It may or may not jump down there. It may continue to next and do 6001, or may jump down to the 460A. And the CPU is constantly jumping around like this. It'll go around in a circle, it'll jump down, it'll jump up, it'll jump around, but it's branching, and the path it goes through is all a single thread, even though it might not do many instructions in a row. It's still the same thread. So this is what CPUs do. CPUs execute and do what the instructions tell them to do and jump around as the instructions tell them to do. And the instructions, and of course, as there's data that gets loaded into it from RAM and ultimately from other hardware inputs, from I/O, from everything from disk drives to serial ports to whatever. The CPU will jump around like that as told. But there is a mechanism in a processor which will break from that strict model of doing what it's told by the instructions and by the data. And this mechanism is called an exception. It's called, in different CPUs, it's called different things. In the ARM literature, and I believe in the older Motorola 68000, this mechanism which breaks the normal pattern of execution is called an exception. And the exceptions are something that happened in the hardware, and it happens for different reasons, which I'll explain in a little bit. But in this case, when the CPU is just humming along, doing what it's told by the instructions, at some point in time it reaches this str.w, which has the first arrow going over to the right to the OS tick. So it's just executing this, and all of a sudden you have what's called the OS tick interrupt. You've got the interrupt which occurs, and this interrupt will tell the CPU, it's the interrupts happening in the hardware, tell the CPU, as soon as you finish the current instruction you're on, stop right there, and I want you to break over and I want you to execute this other path here. And this other path, the source code, is the NUFR plat systic handler. It's the handler for the OS tick, and the instruction starts at 80101FC, the instruction B507. So it will go and do this, and this is actually another thread here, this OS tick handler. It will run through and execute this other thread. When it's finished, we'll go back and return to the next instruction that it would have normally executed but was interrupted from, and this is where we get the term interrupt. So the next instruction is at the address 8010496. It's the move R3 to R2, and the thread which was interrupted will continue executing as though nothing happened, as though it was just paused in time, and what it would have done with the interrupt and without the interrupt will be identical. So understanding exceptions is the foundation to understanding context switches, and also to illustrate how you can have more than one thread that an RTOS or something manages. So a little bit about exceptions. Exceptions are a higher level category of two different things. There are hardware interrupts and software interrupts. Now, the hardware interrupts, of course, are caused by things like GPIO. There's some pins that are attached to the chip. They can be caused by devices which control your disk drives, video, anything like that. All of your hardware devices produce hardware interrupts. Most of them do. I have to correct myself. Software interrupts, on the other hand, are generated either by instructions in the code itself. They are generated by faults, when something goes wrong, the CPU will automatically break the execution and go execute a software interrupt. When a fault happens like that, this is basically a crash. That's the essence of a crash. Other types of software interrupts are interrupts which are used for the kernel. And some of these in older architectures are called traps. Traps are used, I believe all modern operating systems use something like a trap, larger ones that is. I'm talking about Linux, Windows, what have you. They all use traps in order to go from a process into the kernel. So an exception is the only way to disrupt this path of execution. And when an exception happens, the execution will go off and process something called an interrupt service routine, an ISR, which is another piece of code which is reserved for execution when that exception happens. So, as I showed you, you have a thread happening and then an exception happens which breaks from that thread, and then you return to that thread. So when you return to that thread, it should look like nothing happened. There should be no change in what the thread should be doing. In order to pull that off, you have to save some data, because the CPU only can execute natively, and I'll get into this in a little bit, one thread at a time. So you have to, it's kind of like using Windows Notepad in actually in a DOS environment where we only have one window. You save off your file and then you load a different file, but you can only have one file at a time that you're editing. So is the case of the CPU registers. There's one set of registers, typically, isn't a hard and fast rule. Typically one set of registers, which these must be preserved. The values must be preserved when the interrupt service routine is executed. The values which were there before that ISR executes in the thread that was running, those registers must be restored to those values. Otherwise, the thread will detect that something is wrong. And that would also, by the way, cause a crash. And there's another state that has to be preserved in an ISR or on any type of context switch, which is called the task stack. I'll explain that in a little bit. But both of these components are what's known as the thread's context. It's the data which is the state of the thread. It's the data which the thread keeps track of things with, and each thread has its own context, and if that thread is interrupted with the intention of returning to it, that context must be preserved. So a task stack might be a little bit difficult to visualize. I'd cut some corners on this picture to try to illustrate this, and I went to the source code rather than going to the assembler listings. Those of you who are programmers and a little bit about programming, you'll be able to follow this more easily. Others just see what you can pick up. But in this case, let's just say that the execution starts by a call to this second function call, the one in the middle here, which is NUFR semma get W. That's going to be called by some other place, which I'm not showing here, but it gets called, and it proceeds to the execution of the thread, proceeds down, and it reaches this NUFR kernel add task to ready list function call. So function calls, of course, are another way of telling the thread to jump to a different location. In a function call, it's different than a loop, because a function call tells a thread, I want you to jump over here, and then when you're finished, jump right back to where you started the jump in the first place. this function call, which is also called a procedure or a method. This NUFR kernel add task and ready list will direct the thread up to the top here, and I didn't show all the execution, of course, and we'll execute that and return back. Now, what I'm trying to illustrate here is what's shown on the right. So these variables here, starting with the NUFR summa get W function, you've got owner TCB, INV protect, block on summa. These are in the C programming language is what's called an auto storage class. These are actually variables that the thread uses, that it manipulates data when it's executing, and these things are kept on the thread's stack. So what is a stack? A stack is I believe the correct term is a LIFO type of queue. When you put data onto it, in this case, the data is stacked, and this is where we get the term stacked. It's put on it from the bottom up, and then it's taken off from the top down. So as the thread enters functions, it will reserve locations, and the three arrows from the owner TCB, INV protect, and block on summa shows where in memory in the stack. So 1033EC is the memory location for the owner TCB in this case, and these are all numbers I just made up. But you see that there are three slots on the stack which keep the contents of these variables. So when the thread is executing, it's got like a scratch pad location on the stack, and stacks can be anywhere from 256 bytes to several Ks, but it's just a temporary location. It's just a memory location that the operating system maintains for the thread. But with these three locations here, the values of these three variables are saved. So when the thread executes its NUFR kernel add task to ready list and jumps up to the top here to execute down through that function call, the stack will temporarily allocate. It will reserve two more slots for the do switch and priority, which are shown again with the yellow arrows. These two locations cannot use the same locations that owner TCB, invert, protect, and block on summa use, because you don't want to overwrite those other variables. So this is the reason why a stack will, it's called a push operation. It will, every time you make a function call, to reserve more memory on the stack for putting the variables, and then when you return for that NUFR kernel add task and ready list, these two values, the 0 and 8 at the 1033F4 and 1033F0, are discarded, and you return back to the calling function, which is NUFR semaphore get, and your 100204, your owner TCB, invert, protect, block on summa are still there, as though nothing happened. So the stack has to be preserved whenever that thread is switched. So the thread, of course, is a CPU path through assembler instructions, and the thread is that context, the stack and the register values, which that path needs, basically the scratch pad memory that it needs to keep track of things as it's executing. And the way I look at a thread is to take these things which I've explained, all these things. I imagine a thread to be like a train going down a track. Now, of course, I'm not showing the curves in the track, the jumping around. I'm just showing a straight train. Imagine this path that it's the chugga, the train's going down. And Just like a railroad, if there's a rail which is out of place, what happens when you've only got one rail out of place that a train's, on a track that a train's using, and if that rail isn't connected properly, you're going to have a crash of the train. And in a similar way, a thread, if there's one thing that goes wrong, just like that rail went wrong with the train, you'll have a crash of that thread. So, what is context switching? I've gone all through all these details of what a thread is, and of course people have written books about this, explain this in more detail and with more diagrams than I've explained. And I'll say it again, if you really want to understand the thread and context switching, NUFR is written simply. You can just look at the source code. You can run something like GDB or some sort of a debugger and step through it. You can even run NUFR offline, and I've got it set up on a pthread environment that uses DLLs in Windows, free version of Windows Visual Studio, or I'm sorry, Visual C++, and you don't even have to have real hardware. So context switching involves threads and CPUs. Now a thread, a CPU can only execute one thread at a time. And I know what you're thinking. What about multi-core CPUs? So let me qualify this and say this doesn't apply to multi-core CPUs. And some of the other things that I'm talking about don't apply either. The CPUs nowadays have sleep modes, and CPUs can do a few other things, but the older CPUs didn't have all that stuff. So just never mind the power turning off in that. And let's look at these rules here, because these are still relevant even for those CPUs. If a CPU is not asleep, it must be executing some thread. They cannot, it's like a shark. A shark, not all sharks, but there's some type of sharks that if they're not moving, they'll die. So a CPU is the same way. There's always got to be a thread that it's chugging along. And in fact, in NUFR, there's something that I call the background task, which is a thread whose sole purpose in life is to execute when there's nothing else for the CPU to do. When it needs to just spin, so it's like that shark that won't die, it goes to the background task and just spins in a tight little loop forever and ever. A thread can be temporarily suspended and resumed, like I showed with the exceptions. In fact, at the core of it, an exception is the hardware mechanism in the CPU whereby a thread is suspended and resumed. And everything, and on a CPU, everything happens through this suspension and resuming. There are some primitive CPUs where you don't have to have you can do a context switch without having an exception, but I'm not going to cover those. A suspended thread, of course, like I've been saying, it's got to have all of its context properly saved away. And when these conditions are met, this is a context switch. Now, in an RTOS, you will have, and not just an RTOS, but if you consider threads to be ISRs, which you can actually have this in schedulers too, you will have multiple threads that are maintained by a combination of the hardware and the operating system. And of course, only one of these threads will be executing at any given time. The threads, there are threads which the RTOS maintains in addition to ISRs, and that the RTOS has to be sure that the state or the context of all the threads is preserved when these threads aren't running. It's preserved when you do a context switch, when you switch from thread to thread. Of course, this is not just RTOSs which maintain this state. The more advanced operating systems, OSs like Linux and Windows, have to do the same thing. And as I've been saying, the context switch occurs when one thread is halted, excuse me, and another thread is resumed in its place. And a context switch can be from a thread called a task to another task, a thread, the task thread to an ISR thread, ISR to task, ISR to ISR. It doesn't matter. It's all a context switch. But the hardware support for that the CPU has is for ISR switching. Now let me give you a visualization on a context switch. And these arrows here, these black ones going to the right, imagine this is a time axis along the X axis. This is time increasing from left to right. And this is a sequence diagram showing 3 different threads. You've got task A, you've got the software ISR, and then the task B. In this case, task A is running, and then the orange dotted line shows that task A is suspended, and you have a context switch over to the ISR. And the ISR runs for a while and it terminates and has a context switch again to task B. So actually, when task B was suspended before it got switched to by the ISR, and when the ISR tells task B to resume, it will restore its context. So in this sequence, you start with task A that executes, the ISR executes, and then B, which had previously been stopped, had been switched out, gets switched back in again and continues. And each step of the way, A is preserved. The software ISR, you don't have to preserve the state of it. It's designed that way. And then B, which was preserved, is resumed. There are other types of switching. So the previous switch is the full-blown details of what the typical operating system does. There are more simplified diagrams of that where we cut out the ISR step and just show the simple task A to task B switching. In this case, task B runs at a higher priority than task A. And what we're looking at is the guts of multitasking. So you've got 2 threads which are switchable back and forth, whose states are maintained, and the operating system will determine that it needs to suspend task A because task B wants the CPU. In this case, I didn't show it, task B being at the higher priority. I didn't show the priority levels, but if B wants the CPU, the OS is instructed to let it run and to switch to a context switch from task A to task B. Task A gets halted, it gets preserved, and the duration that task B runs, and then when task A resumes, its state is restored, and this is the job of the operating system to go between these. Now, this in a real computer or real processor happens quickly. It can happen thousands of times a second. On a really fast CPU, that can go up to millions of times a second. But this can happen so quickly, it creates the illusion that 2 things are running at the same, 2 tasks are running at the same time. So in a computer, when you're downloading something from the internet and let's say you're downloading from something on the internet, at the same time you're copying a file to a USB drive, at the same time you're listening to watching a presentation on YouTube and listening to the audio, the CPU is switching between all of these tasks very rapidly to give the illusion that it's doing these things in parallel. And again, I say that with multi-core CPUs, it actually is doing things simultaneously, but just pretend like there's no multi-cores, that you're running Linux or Windows or something on a single core CPU. That single CPU would have to jump back and forth whenever you had more data to download. It got more data, it jumps over, it takes that data, stores it away someplace, goes back to showing more of the video, and then it goes over and back and forth, back and forth. So a thread suspension and resumption, a thread must be carefully taken care of. As I said in the beginning, if there's one link, if there's one rail that's out of place in that train which goes down the tracks, you're going to have a crash. Now a thread it must be able to suspend and resume. Suspension and resumption will happen right down at the assembly language level. So any type of thread you have has to be able to have the capability of stopping on a dime, the dime being a single machine instruction, and then picking up where it left off. There's a saving that happens during the suspension and a restoring. And the saved context will also tell you, of course, where you pick up from that execution. So the context switch from from a hardware interrupt will follow a similar sequence to what I showed with these two tasks. You've got task A here. Task A is executing. It's going through. I'm showing this single arrow, but like I showed way back in the beginning, this thing is actually jumping around in loops, function calls. So it's not quite this straight arrow that you see here. But as it is executing, something happens in hardware, and this hardware functionality is independent from what the CPU is doing. So in hardware, a piece of data, let's say, arrives on an I/O channel, and the CPU gets an interrupt from the hardware. The interrupt has an ISR. It handles this new thread that will service this service routine. Gets its name from it. Has to go out to this hardware peripheral and service it. So task A is interrupted by this hardware ISR. And so in time, you see that first orange arrow going down means there is a context switch from task A to the ISR-Z. ISR-Z is executing. When it completes, it might tell the CPU, I want to execute a software ISR. In this case, it's an RTOS kernel call. And this will be an instruction in the ISR, the hardware ISR-Z, to execute this software ISR. Since the software ISR is a higher priority than task A, instead of going back to task A like it normally would, it context switches over to this software ISR, executes that, and then inside of the software ISR, the kernel decides that task B needs to be running. So it finishes saving off everything which task A was doing, because when the ISR happened, actually not everything was saved. Finishes saving that off, puts task B in, and task B begins to run. Now you can see from this diagram that things get more and more complex in a real RTOS and a real operating system on a real system. It's constantly jumping between